Alright guys, you're going to have to bear with me as I do this proof on my computer on a PDF annotator. So, in example 3 on your notes, we're going to prove that the diagonals bisect each other. One thing that's different about this proof then is that if we're going to prove the diagonals bisect each other, we have to draw both diagonals in our proof. Alright, so go ahead and draw both diagonals from A to C and from B to D. Furthermore, where those lines cross, I want you to label as point E. Alright, so right here, this point where they cross, right where my cursor is, I want you to think about that as point E. Now our goal in this proof is to prove that the top triangle, right here, is congruent to this bottom triangle down here. So I want you to just imagine that we're working with the top triangle and the bottom triangle, not the left and the right. And so if we can prove that these top triangles and bottom triangles are congruent, then that would mean these corresponding sides are equal, and these corresponding sides are equal, and therefore we've got a diagonal split in half, and we've got a diagonal split in half. Alright, so that's our goal. Now, easier said than done. First thing I'm going to notice is that we've got vertical angles happening right here in these two triangles. Alright, it's really ugly, but imagine that those are angles 1 and 2. So in my proof down here, I'm going to say that angle 1 is congruent to angle 2 because vertical angles there. Alright, we got vertical angles there. The next thing that you guys are probably familiar with, parallel lines, is going to be alternate interior angles. Okay, so let's imagine that's angle 3, and we know that angle 4 is going to be happening up there. So angles 3 and 4 are going to be equal because they're alternate interior angles. So down here I'm going to write angle 3 is congruent to angle 4. Alright, and excuse my terrible angle symbols, and this guy right here should clearly be a congruent symbol, but I'm typing here so I can't get all of that. So those are alternate interior angles there. Alright, now we have two angles in both triangles. What we don't have though is a pair of sides yet. Alright, we don't have, there's no theorem we know called AAA. Right? We could do alternate interior angles again here and here, but that's not going to do us anything because AAA is not a theorem we know. So we got to talk about the sides. Well, we don't know anything about these sides, since that's actually what we're trying to prove, and we don't know anything about these sides, since that's what we're trying to prove. Do we know anything about the top and bottom sides? Well, this is where it gets a little shady. Back in example 1, you proved the opposite sides were congruent. You proved that these sides right here were equal in a really long proof. We're going to use that proof inside of this proof. So we're actually going to say that BC is congruent to AD. Okay, you're gonna have to hang with me on this one. We're gonna say that BC is congruent to AD. But these two guys are equal here. The reason is, and this is where it's kind of cheap, kind of shady, we're gonna say C example 1. Alright, C example 1. Or if you wanted, you could put like opposite sides of parallelogram are congruent. That actually might be better. You're saying, hey, we already proved this. We don't need to prove it again. We know BC and AD are equal because we proved it before. So therefore, we're going to just transfer that proof down here and say they're still equal. Alright, so those guys are equal. Right, this guy and this guy are equal. If you look at our two triangles then, we've got angle, angle, side. Angle, angle, and then this side down here. So we can say triangle, okay, imagine my triangle symbol there, right? And I'm going to name this triangle BEC, so triangle BEC is equal to triangle DEA by AAS congruency. Alright, imagine my little congruency symbol there as best as I can do it. So AAS congruency. So I have proven that the top triangle is congruent to the bottom triangle. Because I proved that they're equal, that must mean that these sides here are equal and these sides here are equal. You remember what it's called when I say that if I prove the two triangles congruent, then everything about them is congruent? Remember what that's called? So I'm going to say BE is congruent to DE, right? I'm saying that this line is congruent to this line, and I'm saying that AE is congruent to CE by none other than, you guessed it, CPCTC. CPCTC. So by saying these two lines are bisected, or that they're congruent, that they're being bisected, my proof is actually done here. My proof is done. So again, to recap, I proved that this top triangle here is congruent to this bottom triangle here using AAS, angle, vertical angles, angle, alternate interior angles, and side from previous proof. And because they're congruent by AAS, these two sides are equal and these two sides are equal, showing that the diagonals have been bisected.